Now we're beginning a new series. We're beginning a new series of timers and counters, and this is the outline of what we're going to look at. We're going to look at timing without a timer. We're going to look at also timing with timers and counters, and it's very, very much important that you understand that a microcontroller has got what we could delays that could be programmed within a microcontroller, and there's good delays that we can actually program within the software. Now, timing without a counter or timing without a timer, what simply means that we generate the algorithm within the program itself to try to generate a certain delay that we want. Now, this is very important when it comes to timers and counters, because you want to write code that would produce some kind of delay, or you want certain actions to take place after a certain predefined time. For example, you want to switch on an LED. You want an LED to switch on and off every after 1 second, or every after how many milliseconds that you want. So this is very important topic right here, to be able to time our events, to be able to time the operations with the system that we were designing. And this is how this thing comes out. So the course outline, or the outline of what we're going to look at, is exactly what you see right here. Okay. Now we start with timing without a counter, or timing without a timer, and how you want to call it. So this is a sample question that I would like us to look at. So the question says, write a program to blink on and off an LED connected to port D0, as you can see right here, every 1 second. Okay, and you should time this without a dedicated circuitry, or without a dedicated circuitry that is found within a microcontroller. Now, the solution to this problem is actually as the one that you see right here. But of course, the basic things that you see here is that we have the main function that we do, and then we've got the declaration sections. Now we've actually defined our registers, and we've called the temp register to be R16, and we've defined DL1, which is delay 1, to be R17, delay 2 to be R18, and delay 19 to be R19. Now the reason why we've done all of this, we've declared this, because they're going to play a role in trying to design our delay loops that we want to create. Now this is the initialization section, as we all know, but would like to discuss as well what we've done here. Now we've talked about the stack pointer before. Now this way of doing things right here is to try to declare what we call the stack pointer register. Now the reason why we're bringing in the concept of stack pointer register is because we're going to use the stack pointer to use functions such as the call function. Now I want to say that whenever you use the call function, you're trying to tell the program to go and jump to perform a certain section of code whenever the function call is called. Apparently, you cannot call the call function without necessarily declaring what we call the stack pointer. Now the stack pointer is just the area, a certain section in memory that we declare for the purpose of storing temporal variables, or to call certain variables whenever we want to temporarily use them, and then when we need to trash them. So those are actually stored in the stack pointer, and the call function itself, for example, can never be used without necessarily declaring the stack pointer. Apparently, the stack pointer section, the stack pointer itself, has got two registers to go with and we've got what we call a stack pointer low and a stack pointer high. So each microcontroller has got a dedicated section that you need to use for the stack point. But then now you don't necessarily need to remember the lower part of the address and the higher part of the address. So all you need to do is to use the lower element and the higher element. So the lower element has to do with the lower part of the address, regardless of whatever Atmega microcontroller you're doing this. And this, once you do this, it means you're defining that low part of address. And if you're doing this, it means you're defining that higher part of the address. Now, what we've done here to just write SER this simply is self-explanatory. We know that we're declaring this as an output port. Now, this is just an outlier. We didn't need to do this because we're not using port B in this program. All right. Now, as you can see now, of course, we are setting port D as high, and then we are calling the call function. Now, the call function, it goes to perform a certain section of code. In this case, we are calling the delay. If we use the call function without declaring the stack pointer, this would not have worked. It would have generated an error in the compiler. So we are calling, so whenever we write, we set the port D0 high, and then we call the call function. So the call function will come and perform this section of code that we have right here. And whenever it is done, whenever this section of code is done, now already here it's a label. That label is exactly equal to that label, and whatever is under that label will perform. And I want you to remember that at the end of the call function, we have what we call the rate function. So this says return, right? So when you're finished performing what is under that label, you should always remember to return. Now, the point I would like to draw us to is that where does it return to? Well, when you called the delay function, it went to perform, and when it hits eventually the rate function, the rate portion, it's going to return to the next instruction that it should have performed. In other words, you call this delay. Once it is done, it will return not to the call function, it will return to the next instruction it should perform. In other words, it will continue. It goes and performs the delay, reaches the return, then the return will mean that continue to where you ended from. So if it ended from here, it will continue. The next instruction should have performed the CBI. And what that CBI does, it just simply clears, in this case, the port D0. So once you delay, you clear the port, it means that go back now, call the delay once it can perform, meaning delay for 1 second. And then now when you return, now when you reach the return function, return. So now the thing here we forgot in this code is that after you return, you need again to return to, so we need to write here called RIJMP main, because what that means is that it will perform the RIJMP main. When it reaches the RIJMP main, it means again it has to go back to set the port D0 here high, right? So those are the basic things. So here we need to put RIJMP main here. There need to be a function here called RIJMP main that will make us go back to set the port again high, and then so this will be actually in the infinity loop. So real quickly, let me just let's go now to the detailed explanation of how this whole program works. Let's go now to the detailed explanation of how this program works, so that we can get into the intricacies of what this program, what this algorithm, the delay algorithm, is all about. So here is a sample program in which you'll be required to do that. So obviously I've just done .include the program function, and I've done the declaration sections. And these are the registers that I've tried to produce. And on this, there is what we call the start of the program, which jumps to this one. But I want you to see that we're going to have what we declare in this section is what we call the stack pointer. Now the stack pointer has got a lower element and there's a higher element of a stack pointer. Now the reason why we're doing this, and every time you're going to call subroutines, you're going to use the call function, you will need to use the stack pointer because it becomes very handy to call variables in that way. All right, and I talked about the stack pointer a little bit earlier on, but for now just realize that we're going to use it because we're going to be calling certain temporal variables, and therefore we need to declare it. And how we do it, this is exactly how we do it. And then we're going to, in here of course, we're trying to set, you understand, we're trying to set the output port to be the data direction, and here we're trying to also give the status of port B, and which is not really part of the thing here. But the issue here is that we're setting port D0 and then we're calling a 1 second delay, and then we're going to set this one to be low, and then we're calling the 1 second delay as well. Now what we forgot here to put is the RGMP main, because we set the port and then we came to perform the delay time. This is what I need to discuss. So basically what we are saying is that when you call a delay of 1 second, so we are loading into the register DL1, which we declared, we're loading number 8, and this takes about 1 clock cycle, right? And then at delay 1 here, we're loading also in that delay 2, we're looking at 125, and this takes about 1 clock cycle. And then we're loading also 250, and this takes about 1 clock cycle. But I want to explain to you the dec function, which is the decrement function. So, and what it does is that it reduces a particular register, whatever content that is in that particular register, it begins to decrease it. It won't give up decreasing it until that thing reaches 0. So basically what we're saying is that we decrease 250, we start decreasing. When we decrease by 1, and then we come here to a no operation, which again takes about 1 clock cycle. This one takes about 1 clock cycle. And then it says break if not equal to delay 3. So in other words, when it decreases 1, it can perform this. It says if it is not equal to 0, go back to delay 3. Now if you see here, 1 clock cycle for this and 1 clock cycle for that and 2 clock cycles for that, it will do this for 250 times. But 250 times, so this is 1 it comes 1 plus 1 and plus 2, it comes to 4. So the 250 times will be multiplied by these 4, right? And if we have that, that's really a microsecond, because we're using a 1 megahertz of clock. We're saying that 1 megahertz is equal to 1 microsecond. So we're repeating 1 microsecond just by virtue of this internal loop. We're repeating the 1 microsecond, we're repeating it. We're repeating 250 times 4. We're repeating 1 microsecond. Okay, so we're generating, actually what we're doing is that we're having 250, right, times 4, which is 1000. So we're multiplying the 1 microsecond times, we're producing 250 times 4, which is 1000 microseconds. Now 1000 microseconds is basically about, that's a millisecond. So we're producing a millisecond just this delay alone. But what we're looking for a 1 milliseconds. So this branch will only start performing another branch only provided if the 250 has elapsed. And once 250 has elapsed, it has actually repeated these instructions 250 times, and 250 times 4, that's 1. So here now we're decreasing again to 125, and we're saying break if not equal to delay 2. Now this is where the fish comes in. If this is now 1 millisecond, what we are saying is that if we're going to decrease this, and if it's not equal, we're going to again load delay 2 again. And if we reload it again, it to repeat itself for again those times that we have 1 microsecond. So 1 millisecond again will be repeated 125 times. All right, this is what we have. Now we're going to declare 1, and we're going to go 125 times. So I'll be repeated again by this. We shall repeat again by 125 times shall be repeated. 125 milliseconds shall be repeated by 8, which gives us 1 microsecond delay. So basically this explanation is that since that Atmega has an internal running clock frequency of 1 megahertz, clock means this per second, 1 millisecond. So 1 cycle equals to this, and that gives you 1 microsecond. So to get a 1 second, you need of this. So it means that you have to create an algorithm of this building on the example 1 second delay would be as shown below in the written code. Now in this case, there is an internal loop delay 3 that is 4 cycles long. Because dic is 1, no operation is 1, and break if not equals 2, when jumping to delay 3, so 4 cycles repeated 250 times the value of delay 3 are 1000 cycles or 1 millisecond. Then the loop delay 2 repeats the delay 3 125 times the value of this, so the accumulated delay in this case is 125. And finally the loop delay 1 repeats the delay 2 8 times so the accumulated delay in this case is 1000 means or 1 second. Okay on that one.